Welcome to this explainer. Today, we're going to completely change how you look at the abstract math of straight line equations. If you've ever stared at a string of letters and numbers and just wondered how on earth they translate into the physical world, you are absolutely in the right place. We're taking those raw algebraic formulas and turning them into highly visual, concrete geometric models. Let's see how simple equations actually govern the space all around us. Here's our game plan for today. We'll start with the straight line equation, move on to the standard form transformation, tackle drawing line graphs, look at the golden rule of verification, and wrap up with an awesome real-world puzzle modeling plane trails. But before we throw any formulas at you, think about this. How can just two distinct points lock in an infinite, unbending line forever? It's kind of wild, right? Just two tiny dots in the expanse of a grid dictating a trajectory that goes on literally to infinity in both directions. Understanding the mechanics behind this is the key to mastering linear geometry. All right, section 1, the straight line equation. Let's unpack the foundational framework that makes all linear graphs possible. Okay, so any straight line on a flat plane can be written in this general form, y equals mx plus c. Think of this as your universal translator for geometric lines. The m represents our gradient, basically how steep the line is, or how fast it goes up or down. And the c, that's our anchor. It tells us exactly where the line crosses the y-axis, locking its position perfectly in space. So, how do we build this equation from scratch? Well, if we have 2 points, say -3, 3 and 5, 5, we can build it by following 3 really simple steps. First, calculate the gradient, our m. Second, plug in the x and y coordinates of just one of those points. And third, use that to work out the value of c. It is a completely foolproof recipe. Let's see step 1 in action. To find the gradient between our points, -3, 3 and 5, 5, we just look at the difference in their coordinates. The y values jump from 3 to 5, so that's a rise of 2. The x values go from -3 to 5, a run of 8. 2 over 8 simplifies straight down to 1/4, so our m is exactly 1/4. Our line goes up 1 unit for every 4 it moves horizontally. Moving right along to steps 2 and 3. We take 1 point, let's use 5 because positive numbers are just easier to work with, and pop those values back into our working equation. So 5 equals 5/4 plus c. A quick bit of algebra tells us that c has to be 15 over 4. Put it all together, and boom, we've got our complete final equation, y equals 1/4 x plus 15/4. On to section 2, the standard form transformation. This is where we see just how flexible these math rules actually are. You see, we aren't stuck with just one format. We can totally rearrange our gradient intercept form, that y equals mx plus c we were just looking at, into what's called the standard form, which is ax plus by equals c. Why bother doing that? Well, having x and y on the same side opens up completely new ways to analyze the data, especially when you're dealing with multiple equations at once. Let's do a quick transformation together. Taking our previous equation, y equals 1/4 x plus 15/4, we can get rid of those fractions right away by multiplying everything by 4. That leaves us with 4y equals x plus 15. Shift the x over to the left side, and we get -x plus 4y equals 15. And there we are, standard form. Our a is -1, b is 4, and c is 15. Now listen closely, because this is a massive trap a lot of people fall into. The letter c means totally different things depending on the formula you're using. In y equals mx plus c, c is literally the exact spot the line hits the y-axis. But in standard form, that c is just a constant number balancing the equation. It does not automatically mean the y-intercept. Always keep your context straight. Let's hit section 3, drawing line graphs. We are going to take all this theory and turn it into a beautifully drawn visual line. Here's the absolute secret to graphing. You really don't need a massive data set. You don't need 100 plotted points. If you pick just 2 arbitrary x values and find their matching y values, that's it. That is enough to lock in the whole infinite system. 2 points are all it takes to grab your ruler and draw a line that is 100% accurate. Let's look at a super simple example, y equals x plus 3. We just picked 2 easy-to-calculate x values. Let's go with 0 and 4. If we plug in x is 0, y gives us 3. If we plug in x is 4, y becomes 7. Just like that, we have our 2 points, 0, 3, and 4, 7. Plot those, draw a line through them, and you've perfectly graphed the equation. And it works exactly the same way for downward sloping lines. Take y equals negative 2x plus 4. If we set x to 2, the math makes y 0. If we try x as negative 1, well, negative 2 times negative 1 is positive 2. Plus 4 gives us 6. Bam! We've perfectly plotted our downward trajectory with the points 2, 0 and negative 1, 6. Next up, Section 4, the golden rule of verification. Before we finish up our graph and call it a day, we need to talk about an absolute necessity in math. Look, humans make mistakes, right? We drop negative signs, we add things wrong. So while 2 points completely construct the line, the golden rule is to always verify your work with a third, completely separate point. You just visually pick a coordinate off the line you drew and plug it back into your original formula to see if it fits. Let's test this out on our first graph. If we grab a random coordinate off that line, say 1, 4, let's plug it into y equals x plus 3. When x is 1, 1 plus 3 is, yep, 4. The math balances perfectly. It's essentially a built-in insurance policy to prove your visual graph is flawless. Finally, Section 5, modeling plane trails. Let's pivot from the grid and take these concepts straight into the real physical world. If you've ever seen an air show, you know those colored smoke trails are incredible to watch. But to a mathematician, they're basically giant, real-time straight line graphs drawn right across the clouds. Every single plane's flight path has a y-intercept, and their speed and angle represent a distinct mathematical gradient. And depending on their mathematical trajectories, the visuals change dramatically. If 3 planes share the exact same gradient, their trails are totally parallel, meaning 0 intersections. If they angle things a bit, maybe 2 are parallel and 1 cuts across, giving you exactly 2 crossing points. But the really complex, thrilling formations, that's when all 3 intersect to form a triangle, creating exactly 3 crossing points. Which leaves us with this fascinating puzzle to ponder. What specific combination of gradients and y-intercepts would 3 pilots need to coordinate beforehand to make sure their trails cross at exactly 3 distinct points in the sky? It is pretty amazing to realize that the exact same basic equation we just learned is what's used to choreograph multi-million-dollar jets flying at hundreds of miles an hour. Keep an eye out for the math around you, and thanks for joining me on this explainer.